for anyone who's been using our course, which I hope is the majority of you here, work problems are very similar to distance problems. Obviously, you have rate times time is distance, and then you also have, rate times time equals work. The great thing about work problems is that you can develop a very systematic approach to solving them. One of the main components is the combined work formula, where we have work of A plus work of B equals total work. But today I actually want to start off on a slightly different type of problem, and this actually is found in the back end of our chapter. And that type of problem, we call it the multiple worker problem. And I know we like to use a lot of charts and matrices and tables to set up our work problems. It's not to say you can't use it in these scenarios, but it's not something you have to use. But because I'm used to kind of using the chart and table in all of these problems, I'll probably be using it for these. You'll see quite quickly that we don't ultimately use the total work formula to do these, but you'll see there's some really cool ways that I do end up solving them, and it has to do with everything being proportional. So with that in mind, let's get to the first question. All right, so why don't you start with this? Give everyone 2 minutes, and you can type your answers in the chat box. Okay, so that was about 2 minutes. As I said, this is not a type of problem where you would be setting up this combined work formula, but what you see here is that they say 10 men are working at a uniform constant rate. So they're all working at the same rate, and they're doing it at a constant rate. And it's saying that they can dig the ditch in 2 hours. And as I said, is it 100% necessary to use the formula, the table? Not necessarily, but I'm just used to it. So it's something that I feel like anyone should use if you feel like it's going to make your time and effort work a little bit faster when you're on the GMAT. So I have my rate, my time, my work, and what I'm filling in is we're doing the total for 10 men, and then the other category is the rate of the 2 men. Now, we see that 10 men can do a ditch in 2 hours. Now, a ditch is, of course, 1/2, and we need to know how long it will take the 2 men to work at, or excuse me, to do 1/5 of the same ditch. So since we don't know this rate, we can set up a very nice clean proportion that says the rate of 10 men is to a rate of 1/2, as the rate of 2 men is to a rate of X. Now, what I do from here is I immediately cross multiply. You get 10X equals 2 times 1/2, which is 1, or X is 1/10. So what I do is I fill that rate in for the rate of the 2 men, and I see that the work done is 1/5. And remember, time equals work divided by rate. Our work value here is 1/5. Our rate is 1/10. You flip and multiply, you get 1/5 times 10/1. We get an answer of 2. Now, I do realize that this problem dealt with what I would consider, and what most of you would consider, probably some pretty simple numbers. And of course, these problems can get more difficult as you work with harder numbers. So what I want to do is I want to get into a few of those. But basically, you're always looking to use this combined, or excuse me, you're always looking to use this proportion. And the key to understanding that everything is proportional is you see that all of these, workers or machines, they're always working at the exact same rate. So that's always going to be your telltale sign that everything is going to be proportional. So with that said, I want to do one that I think is going to be slightly harder here, but I want everyone to try to use the exact same process that we simply used. So let's try this here. And once again, I'll give everyone about 2 minutes, and then we will move on to a couple more of these. Okay, everyone's try this. Okay, so that was about 2 minutes. What I want to do is I want to really set up and do the same thing that we just did. So you'll notice here, and this is why the proportion is so valuable. So for those who didn't use it previously, obviously I'm okay with that. But, one of the things I always tell my students is I want you to use methods that you know are going to work time and time again. So if one item is changed and now all of a sudden you can't do this problem, then, obviously I'd like you to use my method. But remember, I'm never dead set on saying it's my way or the highway. I want everyone to be successful, and obviously Scott and myself are here to teach you what we feel are best practices. In any time you can be systematic, I feel like that's obviously a best practice. So what I do is I have my rate, my time, my work. I notice that I have 8 logging machines here for the first row, and then I have X logging machines here for the bottom row. Now, we are given that 8 logging machines can complete 15 loads in 45 days. So that's 15 over 45, and that gives you 1/3 as a rate. Now, this is where things get a little trickier. It says how many more logging machines, also each working at that same rate, would have to be used to complete, and here's the key word, same number of loads. So the initial number of loads was 15. So it's saying same number of loads in 20 days. We reduce that and we get 3/4, and you'll notice the unknown in our proportion is no longer the rate in the second row, it's the number of logging machines in the second row. So now we very easily and clearly say 8 is to 1/3 as X is to 3/4. I once again cross multiply, and I get 24/4 equals X/3. Of course, 24/4 is 6, so 6 equals X/3, and then if we move this over to the left, 18 equals X. Now, I'm happy that no one put D as an answer, which means everyone here has been trained very well, and everyone is not falling for trap answers. A lot of times what we'll do is we'll see a value, we'll think we're done, but obviously it says how many more logging machines we see. Initially there were 8, we went to 18, so of course that's 10 more than 8, and the answer here is 10. So hopefully everyone appreciated using the method I taught you in this question. I'd like to do one more so everyone can get really good practice here, and this is more similar to the first one we did with simply more challenging numbers. So I'll give everyone 2 minutes to work on this. Give me 1 sec. Okay, so hopefully, as I said, everyone is using a similar method to what we originally did. I set this up, I create my box here, and in my box, I know right away it's going to be something to do with the men, or the people in this case. So we have 6 people, and we have 8 people. Okay. And then we're going to start filling in. So we have a rate, a time, a work, and we see that 6 people, each working at the same constant rate, can do 12 houses in 24 hours. So 12 over 24, that's 1/2 is the rate. And next, we're trying to determine the rate for the 8 people. So once again, we want to use our proportion. We have 6 is to 1/2, and notice I'm kind of saying this out loud. If I'm on the GMAT, am I saying it out loud? Probably not, because people will get annoyed at me, but I'm probably doing this in my head. I like to sound things out so they come out clean on the page. So 6 is to 1/2, as 8 is to x, and then immediately I jump into my cross multiplication. 6x equals 8 times 1/2, which we know is 4, or x equals 4 over 6, which is 2 over 3. So we plug that into our box here, and it's saying how long would it take those 8 people to clean the same number of houses. We see once again that is 12 houses, and we know time is work divided by rate. The work value here is 12. We have 2 over 3 as our rate. Flip and multiply. We have 12 over 1 times 3 over 2. So as you can see, that ends up being 18 hours. Now, for anyone here who had trouble following this method, we have a lot of these questions in our work chapter. Work questions are very interesting because, as I said, most of the work chapter is dedicated to using either the combined work formula, where you're adding the works together, setting it equal to the total work and solving, or the opposing work formula, which is just simply almost the same process, except you're subtracting. And then this is kind of its own entity, and as I said, there's many keys to recognizing what you're dealing with here, because a lot of times you're dealing with multiple people or multiple machines. You'll see that they're working at the same constant rate or at a uniform constant rate, and so you'll know to use this method. And furthermore, proportions can be used in many places on the GMAT. For instance, if you're given that you're filling up a tub, and you know that and you're filling it at a constant rate, if you know that 1/3 of the tub is filled up in, say, 5 minutes, you can then determine how long it will take to fill up the entire tub by using proportions. And it all stems from the fact that everything is being done at a complete constant rate. So if you're not already using proportions, it's something that I think can benefit you greatly. And 110%, if everyone here can get this method down on these types of questions, these will literally be gimmies for you on the GMAT. And these are questions that I believe a lot of people struggle with who don't have a sound method in place to use them. So for all of you using our curriculum, go back, practice a bunch of these questions, go to your on target, and you'll definitely be able to find more to practice and see how this method works for you, moving forward. So with that said, I want to turn things over to Scott. I know he has some nice, challenging work problems to give you. So Scott, if you want to get moving with some of those, you can take it away.
Hey, thanks, Jeff. How's my audio this morning?
Yeah, it was good, which is a good thing.
Good. Okay, guys. Thanks a lot, Jeff, for all that great learning you gave us. Morning, everybody. Thanks so much for coming. What we're going to do is we're not necessarily going to do anything more difficult because the nice thing about work problems is they're really systematic and they're mechanical, And for any of you who have been studying for the test for a while, you know that anything that's systematic or mechanical has to be our friend, because there's enough stuff on the test that is esoteric and is so variable that we love the opportunity to just have a system in place where, you know, we have a set number of go-to best practices we employ, and if we do those precisely and accurately, we get the right answer. And I feel like work problems are one of those types of problems. So what I'm going to do, as I said, not necessarily make these really difficult, but I just want to give you a broad sampling of the types of work problems that you can encounter. And we'll shoot for between, say, 2 and 3 minutes on these guys. They're word problems, so sometimes they take a little longer, especially if you're just getting started studying. But why don't we set our clocks or iPhones, whatever you're using, for, let's say, 2 to 3 minutes, and we'll start now. And you can put the answer in the chat box whenever you have it. Okay, guys, that was a little bit over 2 minutes. So let's go through this. And I'm not actually going to make the matrix box just because it's probably a little bit of an extra step we don't need to do. So once, we should absolutely use the matrix approach, but once you have seen what the box looks like, you can maybe get away with not drawing it as long as you're careful with the rows and columns. So what we have here is Carla and Dan. And we have some given information we should always put in. So first we're told that Carla can wash a load of dishes in 42 minutes. Well, we're given a time, but what that means is her rate is one job in 42 minutes. Right? If it takes her 42 minutes to do one load of dishes, well, one load, it doesn't matter that she's doing dishes or if she was painting houses or washing cars or digging ditches, doesn't matter, or making necklaces or anything else for that matter. It's one job in 42 minutes. So the rate is 1 over 42. Now, we basically need to know Dan's time, right? How long would it take Dan to wash the load of dishes by himself? So we can let Dan's time be D or T. So here, let's call it T. So we'll say Dan's time is T. And if that's the case, his rate becomes 1 over T, okay, where T is what we're actually looking to solve. Now, we're told that it takes them 28 minutes to wash the same load of dishes. So they're working together for a time of 28 minutes. And I didn't say this at the beginning, but I think just remember that rate times time is equal to work. Okay, rate times time is equal to work. So what does that mean? Well, it means that Carla's work done is 28 over 42. And Dan's work done is 28 over T. Okay, so what we know, what we know is that the work from Carla plus the work from Dan has to equal the total work, right? And that's an intuitive equation because what else would equal the total work if it were not the work from Carla added to the work from Dan? Okay, so that's easy. So that's 28 over 42 plus 28 over T, and they're doing one job. Okay, they're going to do one total job, and that job, of course, is the load of dishes. Okay, so this reduces, this is 2/3 plus 28 over T is equal to 1. Now what we'll do is we want to get rid of these fractions right away as soon as possible. So what we'll do is we'll multiply the entire equation, each term by, that's not an x to t, by 3t, because 3t, guys, is the least common denominator here. And remember that 3t has to multiply by this term, by this term, and by this term. And when we do that, what do we get? We get 2t plus 84 is equal to 3t, and t is equal to 84 minutes. And because we let t be Dan's time, we can see very easily that it would take Dan 84 minutes to do this job by himself. So it's a classic type of work problem where we have one of the times unknown. So take a minute, take that down, take any notes down on that you like. And the next problem we're going to do is more difficult. It's in the form of data sufficiency. Now, the key in this next problem is to just take it systematically. And remember, guys, like we all know we don't have to get an answer with a data sufficiency, but it doesn't mean that we don't have to do work. So if you're not writing ink on the page for this problem, you're not deeply analyzing the problem enough. So this is going to take some work, and it's going to take some ink. So let's take it away starting now. Okay, guys, that's about 3 minutes. I want to give you extra time to see if you make some progress on this. So we have machines A and B producing shoes, and each machine must produce W shoes while working alone at its own constant rate. So what's the rate of machine A? All right, so statement 1, machine A's rate is 1/4 of machine B's rate. So we can just quickly evaluate these guys. We can say A and B. We can say rate times time is equal to work. And we'll let machine B's rate be B, and then machine A's rate is 1/4 B, right? Because machine A's rate is 1/4 of B's rate. Now, we know they each produce W shoes, so let's just say we have W shoes as the work of A, and W shoes for the work of B. Well, remember, guys, time is simply equal to work divided by rate, so we can use these variables to kind of work inwards here to see that the time of A would be, well, that would reduce to 4W over B after we flipped and multiplied by the 1/4. And this is W over B. And we want to know what's the rate of machine A. Well, we have 4W over B. We have W over B, right? It's kind of like a time of A, and there's a time of B. But without more data, there's nothing we can do with these guys, right? It's difficult to come up with a numerical value here. It's just variables, right? Remember, as a data sufficiency question, we absolutely need to see whether we can get a unique constant value. So this is not going to work. Nothing we can do here. So we'll say A and D are out, and we're down to either B, C, or E. All right, statement 2. So it takes machine B 6W fewer hours to produce W shoes than it takes machine A to produce the same number of shoes. Okay. So most of you can see by looking at this, there's just really nothing here at all we're going to be able to do. It just gives us a relative relationship between the time it takes machine B to produce the shoes and the time it takes A. But there's a lot of things that could be there for W. So most of you, I think not all of you, can see that statement too. It's just not going to yield anything fruitful for us. So B is out. Now, most students who answer this question actually say that the answer is E as in echo. But the answer is actually C as in Charlie. Let me show you why. So the reason why it's C is we just determined that one of the guys' times was W over B, and the other one was 4W over B, right? So we knew that, and we didn't know the equal sign, but we knew we had those 2 times, right? And then 2 says it takes B 6W fewer hours to produce W shoes than it takes A. So what we can say here is that W over B is equal to 4W over B minus 6W. Right? Because it says it takes machine B 6W fewer hours. Right? And what's interesting is that it's expressed in terms of W, which is always something to be on the lookout for. Right? So in other words, here's the time of machine A right here. Here's the time of machine B. And it takes machine B 6W fewer hours than it takes machine A. Now, if you sort of underanalyze this, what you're going to say is that there are 2 variables and there's only 1 equation. And if we did that, we wouldn't be correct, because on a little bit of a more careful analysis, we can see that that W exists in every term, so that W can go away. Right, it will be down to 1 variable. So I'll solve it for you for your learning benefit. But we wouldn't have to if it were the actual test, right? So what I'll do is I'll multiply it by B to get rid of the denominator. and we'll get W is equal to 4W minus 6WB. Okay, so what we'll do is we'll get rid of divide by the W's. We'll say 1 is equal to 4 minus 6B. We'll say that 6B is equal to 3, or B is equal to 1/2. Okay, so what we know then is the rate of B is 1/2 of a shoe per hour. So then the rate of A must be 1/2 times 1/4, which is 1/8 of a shoe per hour, right? Because the rate of A is 1/4 of the rate of B. Now again, guys, like you don't have to do this on the test. You should only take the data sufficiency as far as to the point where you know you could actually either get a value or you wouldn't be able to get a value. But for your learning, I want to solve it fully through. So you got to be careful with data sufficiency. We talked before about the type 1, type 2 lines of thinking. I'm not going to go through that again now just because it's a long discussion. It's uber helpful. So if you haven't heard about sort of my spiel on type 1, type 2 thinking and you want to know more about it, just send me an email, scott@targettestprep.com. I'd be happy to talk about it with you. Okay, so this is a common one. Again, the key here was that one of the pieces of information were expressed in terms of another. Okay, let's do another one that's a little bit more complicated. Let's do a problem solving, and I'll definitely give you 3 minutes for this. Go carefully, go accurately, and we'll start now. Okay, guys, that was about 3 minutes. Again, I want to make sure I give you guys enough time to practice this stuff. So we have a dad and the son, and they're shoveling snow off a driveway. They can shovel all the snow in 24 minutes. And if the son works alone, it takes him 20 more minutes than it would take the dad. So we want to know how long does it take the dad to shovel snow. So we'll say we have the son and we have the dad. And from there, we'll say we have rate multiplied by time. We know will give us work. Now, the tough part here is setting up the rate. So what we can do here is let's let t be the dad's time, right? So then the dad's rate is 1 over t. Okay, so the dad's time is t, and then the dad's rate is 1 over t. So then if it takes the son 20 more minutes to shovel the driveway, well then the son's rate is 1 over t plus 20, right? Because the dad's time would be t, and the son's time would be t plus 20. So therefore the rate of the dad is 1 over t, and the rate of the son is 1 over t plus 20. Okay, and when they work together, it takes them 24 minutes. So that means that the son, remember rate times time is work, so the son does 24 divided by t plus 20 of the job, and the dad does 24 over t of the job. Okay, now notice here, guys, that the son is actually doing less work, right? Because the t plus 20 is a bigger denominator than t, and the numerators are the same. So it clearly further supports the idea that the dad's working at a faster rate. He's doing more work. Okay, so remember the work from the son plus the work from the dad has to equal the total work, right? And that's an intuitive equation, as always, because what else would equal the total work? If it's not the work of the son plus the work of the dad, what is it? So work of son plus work of dad is work total. Now, here's the next part students have trouble with, but it's very simple. What we need to say to ourselves is that the work of the son, 24 over t plus 20, plus the work of the dad, 24 over t, is equal to 1. And I don't know why, in general, some students have a hard time seeing that that's a 1. It's just one job. It's one driveway. You know, it doesn't matter what it is. It could be eating one sandwich. It could be drinking one root beer. It could be, mowing one lawn. Really, the work that's being done doesn't matter. What matters is it's one job. And now it's just careful algebra. So we have a nice quadratic here, and we're going to first get rid of the denominators. I don't like looking at those, and neither should you. So the least common denominator, in other words, the first number that both of those two denominators, t plus 20 and t will divide into, is t times t plus 20. Okay, and remember, guys, this has to multiply by each term in the equation. So we're going to do 3 multiplications. And when we do that, we're going to be left with 24t plus 24 times t plus 20 equals t times t plus 20. Okay? Distribute that 24 through, so it's 24t plus 24t plus, what's that, 480 is equal to, now put that t through, so that's t squared plus 20t. We'll combine a bunch of like terms here. Will leave us with t, well, actually, let's do one step prior so we actually, we see exactly what's going on. So that would be 48t plus 480 is equal to t squared plus 20t. We'll now collect all the like terms. That will be t squared minus 28t minus 480. And guys, because it's a quadratic, we'll set it equal to 0. And of course, now we'll get our roots. So it could be t minus 40, t plus 12 is equal to 0. or t is 40, or t is minus 12, theoretically, but in a work problem, the time can't be negative. So what that means is that t is equal to 40. The time is equal to 40. And let's go up, and let's really hope there's an answer choice of 40. Yes, there is. After doing all that work, I want to make sure we get it right. So this is a more difficult work problem, but if you're shooting for a high score, it's one you need to master. And here's a little important insight. Self-awareness is important. If you look at this and you either say, ooh, that didn't feel very comfortable, or you said, wait a minute, that's too tough for the GMAT. Either way, you know there's a red flag going up that you have to be aware of. So this is definitely something you would need to understand if you're shooting for a good score. So it's something you want to work towards. And if you're feeling uncomfortable with it, if you've seen something like this before in the test, or you know it comes up on the test in some shape or form, but you know, you're just feeling uncomfortable with it, then it's just practice. It's like anything else, guys. Test is very predictable, it's very beatable. You just got to work at this stuff, and the more you touch and the more you see, the better the test is going to go for you. So we appreciate you guys coming. You know, you can check us out anytime. You can send us an email if you have questions, whatever you need. We want you guys to all be successful. And with that, we wish you all a good day. And you know, I know you had better things you could have done this morning, so we do appreciate you hanging out with us. And with that said, we'll talk to you all same time, same place next week. Okay, take it easy, everybody.